Hello and welcome. In this lesson, we shall learn about the memory organization of AVR CPUs. The AVR core has three memory spaces: 1. Data memory, 2. Program memory, and 3. EEPROM memory. The data memory space is mapped to general purpose register file, IO register, extended IO register, and SRAM. Flash provides the program memory and stores the program downloaded to the microcontroller. The memory spaces are physically separate and the address spaces do not overlap. ATmega 328 also provides EEPROM to store data required across the system reboots. The data memory space is byte addressable and organized into different regions. The first 32 address locations, that is the address starting from 0x00 to 0x1f, are mapped to the general purpose registers. These 32 addresses are bit accessible using instructions set bit in IO register SBI and clear bit in IO register CBI. The value of single bits can be checked using SBIS and SPIC instructions. The next 64 address locations starting from the address 0x20 to 0x5f are mapped to IO register. Some CPU registers are also mapped to this address space. For example, the 2 bytes of stack pointer SPH and SPL with the addresses 0x5e and 0x5d belongs to this address space. The data, address, and control registers of various peripherals are also mapped to this memory region. For instance, the 2 bytes address, data, and control registers used to read, write, and erase the EEPROM are mapped to this address space. The registers in this region can be used with load store and in-out instructions. That means the registers mapped to this space are memory mapped and IO mapped. The next set of 160 registers are extended IO registers, which occupies the address 0x30 through 0xFF. Similar to IO registers, the registers mapped to this address space are also used to communicate with peripherals. However, there is a difference. The registers in extended IO can be accessed using load store instructions only. That is, these registers are memory mapped. The next 2K address locations are mapped to SRAM. This is the region of data memory where all the variables, stack, and heap are allocated during program execution. The on-chip SRAM access for either read or write operation is performed in 2 clock cycles. In the first clock cycle, the address of the memory location is computed and placed in the address bus. And when the control line is enabled, the content of the address is available. The line WR is used as write control line and RD is used as read control line. The 32 kilobyte on-chip in-system programmable flash memory is mapped to the program memory space. The program memory space is word addressable and arranged as 16-bit 16K addresses. Whenever the MCU is powered on or reset, the program counter starts fetching the instructions from the address 0x00 of the flash memory and executes those. The PC is 14 bits wide, thus addressing the 16K program memory space. For software security, the program memory space is divided into 2 sections: bootloader section and application program section. The size of the different sections is configured by the boot size fuse bit. These 2 sections can have different level of protection since they have different sets of lock bits. The application section is used for storing the application code. The protection level of the application section can be selected by the application boot lock bits. The application section can't store bootloader code since the instruction Store Program Memory (SPM) is disabled when executed from the application section. The instruction SPM is used to program the flash memory. The bootloader section stores the bootloader program. It is a special program which interacts with the software running on the development PC over serial communication channel to download and flash the application program. This avoids the need of external programmer. The instruction SPM can only be executed from the boot flash section. There are two things you must have noticed. The first is the registers mapped to the I/O memory space in data space have two offsets. For example, the status register SRES has offset 0x5F and 0x3F. Similarly, the high byte of stack pointer SPH has two offsets 0x5E and 0x3E, and the low byte SPL has offsets 0x5D and 0x3D. On the contrary, the extended I/O register is accessed using only one offset. For instance, the watchdog timer control register has offset 0x60 only. And second, the I/O registers can be manipulated using the load store and in-out instructions. However, the extended I/O registers can be manipulated using load store instructions only. How can these be explained? The peripherals communicate to the microcontroller through registers which are accessible to both the devices. Some microcontrollers have dedicated address space to which the peripheral registers must be mapped. This is called I/O space and accessed using the in-out instructions only. And other microcontrollers allow peripheral registers to be mapped to the CPU's memory space. These memory addresses are read and written using load store instructions, which are generally used to move data between memory and register file and vice versa. The first mapping is called I/O mapped I/O and the second is called memory mapped I/O. I/O mapped I/O is also called isolated I/O since the I/O space is isolated from the CPU's address space. The Atmega 328 microcontroller supports both the I/O mapping mechanism and supports load store and in-out instructions. The I/O registers are mapped using the Atmega 328 microcontroller supports both the I/O mapping mechanism and supports load store and in-out instructions. The I/O registers are mapped using both the mapping mechanisms, whereas the extended I/O registers are mapped using memory mapped I/O. With this, we have come to the end of this lesson. Thank you.